On this channel, I've made many chemicals, and some of them have smelled really nice, like grape or wintergreen, and others have smelled terrible, like putrescine or scatol. And in theory, I could have used any of these to make a perfume, or I could have mixed them all together to make some sort of disgusting creation. However, I thought that maybe it could be fun to make a completely new one, and I decided to go with raspberry ketone. Raspberry ketone occurs naturally in red raspberries, and it's a major component of their smell. The amount in the raspberries, though, is really small, and it's estimated that 1 kilo of raspberries might only contain a few milligrams of it. This makes extracting it extremely inefficient and way too expensive to use in things like candy or food. This isn't really much of an issue though, because with chemistry, we can often just disregard nature and build the molecules ourselves. And like with many other flavors, fragrances, and pharmaceuticals, the building process usually starts with some sort of cheap petroleum product. For any given molecule, there are many ways that it can be built, but for raspberry ketone, this seems to be the common pathway. It starts with benzene, which is derived from crude oil, and with every step, the raspberry ketone molecule is slowly put together. This is a really long and labor-intensive process though, and when producing it industrially, nobody's going to be starting with benzene. Like with most other syntheses, they'll start with the cheapest mass-produced precursor that's closest to the final molecule. In this case, it's often 4-hydroxybenzaldehyde, so that's what I'm going to be starting with. As usual, I tried my best to find an easy online source for this chemical, but unfortunately, I wasn't able to find a single place. So I didn't really have a choice, and I ended up having to order it from Sigma. Before I get started though, I did just want to say that making raspberry ketone myself isn't the most efficient way to get it. The entire point of this project was just to explore the chemistry and the science behind its production, and to just have fun making it myself. Unlike the 4-hydroxybenzaldehyde, the raspberry ketone's actually quite easy to find online. There are a lot of places that sell it for relatively cheap, but it's not meant to be used in food or perfume or anything else like that. It's instead sold as a weight loss supplement, but as far as I know, as with a lot of other weight loss supplements, there's no real evidence that it actually works. However, it was convenient for me to have an easy and pure source of the ketone, and you'll see later on in the video how I take advantage of this. But anyway, with that being said, we can finally get started. The first step was to make a dilute solution of sodium hydroxide, so I added about 4 grams of it to a beaker, followed by 40 ml of water. I swirled it around a bit over the course of a couple minutes, and eventually it all dissolved. I didn't need this solution right at the moment though, so it was temporarily placed on the side. I then got a flask, and I dumped in 10 grams of the 4-hydroxybenzaldehyde. On top of this, I dropped in a stir bar, and I also added 40 milliliters of acetone. It quickly dissolved a lot of the 4-hydroxybenzaldehyde, but to get the rest of it, I had to turn on the stirring. In less than a minute later, it had all disappeared, and I was left with this crystal clear solution. Now the next step was with strong stirring to slowly add the sodium hydroxide solution that I just made before. This caused its color to slowly change, and by the time that it was all added, it had turned yellow. What's going on here is a reaction between the acetone and the 4-hydroxybenzaldehyde, and it's catalyzed by the sodium hydroxide. This reaction is generally known as an aldol condensation, and a new carbon-carbon bond is forming between the two molecules. The result is this intermediate molecule, which is actually very close to the final raspberry ketone. However, it still has this double bond, which I'll have to get rid of with another reaction. This intermediate has a slight yellow color, and I think it's why the color of the solution changes. This reaction's a bit messy though, and it forms side products and tar, which I think cause it to slowly turn red. At this point, I sealed it with a stopper, took it off the stir plate, and I let it sit somewhere dark for about 24 hours. During this time, the reaction slowly went to completion, and when I came back to it, it had almost completely solidified. Now into a beaker, I added about 100 ml of water, followed by 65 ml of concentrated hydrochloric acid. This was then topped off to about 200 ml, and it gave me roughly a 10% solution. This was all mixed together as thoroughly as possible, and I also added some ice. Then I shook the reaction mixture to break up all the solid stuff, and I poured it into the acid. The major reason for this step was to help purify out the raspberry ketone. I also washed the flask a couple times with water just to get out as much as possible. This reaction isn't very clean, and the base causes some of the acetone and our product to polymerize. Our desired product should have an off-white or slightly yellow color, and I think that all this red stuff is just polymerized junk. By adding it to the acid, all the sodium hydroxide is being neutralized, and it stops things from polymerizing more. Also, the water dissolves the leftover acetone, which helps separate the product from the tar. This process didn't happen instantly though, and the product just slowly crystallized out over the course of about 10 minutes. When it looked like it was done, it was time to get rid of all the water, and I did this by vacuum filtration. So I turned on my vacuum pump, and I started adding the mixture. When everything had been pulled through, I washed the beaker and the powder with some more water. Then I turned on my pump again, and I let it run for a couple minutes. I was eventually left with a reddish-brown, semi-dry powder, but it was still really impure. To clean it up, I just had to recrystallize it, so I poured it all into a beaker. Then I added a somewhat arbitrary amount of water, and I turned on the stirring and heating. As it warmed up and got closer to the boiling point, more and more solid dissolved, and it took on this green color. Also, at some point, all the solid had melted, and it became an oily liquid. Most of it eventually disappeared, but to get the rest, I had to start adding more water. I ended up adding quite a bit, and at this point it looked pretty good, but there was still a small amount left. I really wanted it to be nice and clear, but this would require adding more water, and I worried it wouldn't fit in the beaker. So I just quickly transferred it to a larger flask, and then continued adding more. It did end up clearing up completely, but it also didn't take that much more water, so probably everything would have fit in the beaker, but oh well. I then took it off the hot plate, pulled out my stir bar, and waited for it to cool down. When I came back the next day, I had a lot of nice whitish yellow crystals, but there was also a lot of this nasty junk on the bottom. All that stuff is just a mixture of the product, as well as tar and other things, and it's gonna have to be processed again. The fluffy crystals though are still good, and they can just be filtered off. And I did this just like before, using my vacuum filter. And after all the water was pulled through, I washed it with more water, and I left the pump on for a few minutes to dry it up as much as possible. I'm not sure why, but by the time I was done with it, it wasn't white anymore, and it had turned yellow. I then dumped it onto some paper to dry, and at this point, it even looked orange, but by the next day, it was back to being a pale yellow. In total here, my yield was about 3 grams, which was a bit low for this reaction. Also, the purity of the stuff here was decent, but it wasn't as good as I would have liked, so I wanted to clean it up a bit more. First though, I wanted to see if I could increase my yield by getting more product out of the tar junk, and I'll come back to this in a bit. All of the tar had solidified, and was only loosely stuck to the bottom, so it was pretty easy to scrape off. To get it all out, I ended up having to wash the flask a few times with water, and all of these washings were added to a beaker. The heating was turned on, and like before, I kept adding small amounts of water. Eventually, almost everything dissolved, but there was still some stubborn tar at the bottom that didn't seem to disappear even when I added more water. So I decided to get rid of it, and I did this by pouring everything into another beaker and doing my best to not include the tar. I then added a bit more water and brought it to a boil, and I was left with a crystal clear solution. This was taken off the hot plate and the stir bar was removed, and I waited for it to cool to room temperature. I ended up leaving it overnight, and when I came back the next day, I saw that some really nice crystals had formed. Unfortunately though, there was still a decent amount of tar junk at the bottom. But thankfully, it was pretty easy to separate from the crystals, and I just had to shake it around a bit. I then filtered it off and dried it like we saw before, and this is what I was left with. I was able to recover another gram of the product, which was pretty significant considering my initial yield was only 3. Now the total amount that I had was 4 grams, but like I said before, it wasn't as pure as I would have liked, so I had to clean it up a bit. To do this, I had to do another recrystallization, but this time, instead of just using water, I decided to try a mixture of water and ethanol. I started by adding a somewhat random amount of ethanol, and then I turned on the stirring and heating, and I waited for it to get to a boil. The raspberry ketone and most of the impurities are much more soluble in ethanol, so this time they dissolved relatively quickly. When it eventually got to a boil a few minutes later, I started adding water to knock down the solubility. The basic goal here was to keep adding the water in small portions until the product was just barely soluble in the boiling solution. When I eventually got to what I felt was a good balance between the ethanol and the water, I took it off the hot plate. I took out the stir bar and let it cool, and several hours later, I had these nice white crystals. At the bottom, though, I unfortunately still had some tar. But in any case, I just swirled it around like before to separate the crystals, and I filtered them off. I let them dry for about a day or so, and I was left with about 3.75 grams. This was definitely way more pure than before, but it still looked like there was a bit of orange stuff in it. But despite this, it was more than pure enough for the next step, so I decided to move on. What I thought was interesting was, as I mentioned before, this molecule is extremely close to raspberry ketone. However, despite just being one double bond away, it really had no smell to it. The next reaction that I had to do was known as a reduction, and to do it, I needed hydrogen gas. However, I didn't just have a tank of it lying around or something, and I had to make it myself. In a lab setting, there are several ways that this can be done, but I found that for me, the easiest one was always just to mix sodium hydroxide drain cleaner with aluminum foil. This was the setup that I put together, which at first might look a bit complicated, but it's really not that bad. The basic idea is that the flask is filled with aluminum foil, and then above this, I've attached an addition funnel. And in this funnel is a whole bunch of concentrated sodium hydroxide solution, so when it's opened, it'll all start dripping on the aluminum foil. When they come into contact, they'll start to react, and they'll produce hydrogen gas, which will be pushed out of the flask. It'll then move through the plastic tube and into my trap, which I've filled with calcium chloride. The calcium chloride is a dehydrated salt, and it'll pull a lot of the water from the hydrogen as it passes over it. This will by no means completely dry the hydrogen, but it should take away most of the moisture. After generating a decent amount of hydrogen and letting all of the air get pushed out of the system, I attached a balloon. When it got to a decent size, I took it off and I sealed it by just wrapping it around a glass stopper. Then I attached another balloon and kept collecting the hydrogen. One thing that I do want to mention though is the major downside of this reaction, which is that aluminum and sodium hydroxide generate a lot of heat when they react. This means that as the reaction continues, things get hotter and hotter and more water is passed over with the hydrogen. For the most part, the calcium chloride does a decent job at picking this up, but it can very easily get overwhelmed. To deal with this, one relatively easy method is to just put a condenser above the flask to try to recondense as much of the water as possible. I went for the even easier method though, which was just to occasionally cool the flask with a bit of cold water in a bowl. But anyway, with the hydrogen now ready, I was able to move on to the actual reaction. So into a flask I added all the intermediate that I made before, along with some ethyl acetate. I then turned on the stirring, and when it all dissolved, I added 4 grams of anhydrous sodium acetate. I actually made this myself by mixing vinegar with baking soda, boiling off the water, and then drying the powder that was left over. This isn't soluble in sodium acetate though, and it just has to be kept in suspension with strong stirring. Then on top of all of this, I added 0.4 grams of something called palladium on carbon. This is the active catalyst for the reduction reaction, and like the sodium acetate, it isn't soluble, so it's just kept in suspension. Now with everything added, it was time to put together the rest of the setup. This is the way that I like to put it together, and it's just based on the glassware that I have available. The piece that I'm adding here has 2 adapters that I can attach a hose to, and it's hard to see at the top, but it's sealed with a stopper. All of the glass joints are also sealed with grease to make sure that there aren't any leaks. Then to the lower adapter, I attached a hose that led to a vacuum pump. And to the other one, I put on a hose that led to my hydrogen balloon. I also attached some plastic clips to all the joints, just to make sure that they didn't pop apart. Okay, so at this point, things were looking pretty good, but before I could get started, there was just one last thing that I had to do. I made sure the valve to the balloon was closed, and I opened up the vacuum one, and I turned on my pump. I let it go for a few minutes to pull as good of a vacuum as possible, and then I shut the valve. Now with the whole system under vacuum, I opened up the valve to the balloon, and I filled it with hydrogen. When the balloon stopped shrinking, I closed the valve again, and then I opened up the one to my vacuum pump, and I pulled another vacuum. This whole cycle was repeated 2 more times, just to make sure that there was no air in the system. This is extremely important because if there's any oxygen present, the palladium on carbon can sometimes ignite the hydrogen. And if there's enough and this happens in a closed system, it can lead to a pretty nasty explosion. I did my cycles by filling it with hydrogen, but generally, it is better to use nitrogen. To do this, I would have needed a third hose adapter, and I would have just done my cycles and flushed it every time with nitrogen. Then, as a final fourth one, I would have pulled out all the nitrogen with my vacuum and filled it with hydrogen. That method is technically safer because there's never any risk of having hydrogen and oxygen in the system at the same time. However, my vacuum pump is decent enough, and I've never really had an issue just cycling it with hydrogen. But anyway, after pulling a vacuum on my system for the third time, I opened the valve to my balloon, and I just kept it like that. At this point, it doesn't really look like much is happening, but the reaction is occurring. The palladium on carbon, which is basically just palladium dispersed on carbon powder, is catalyzing the breakdown of the hydrogen and its addition to the intermediate molecule. As this happened, the hydrogen was slowly absorbed and the balloon shrank. Most of the hydrogen eventually disappeared, so I shut the valve, took off the balloon, and replaced it with a fresh one. Under normal conditions, hydrogen gas exists as H2, and it's not that reactive. The bond between the hydrogen atoms is relatively stable, and it doesn't really want to break apart and react with other things. So to make this happen, energy needs to be put in to break these atoms apart, which is why it doesn't just spontaneously burst into flames in air, and it needs some sort of ignition source. For most reactions, though, we don't really want to deal with any fires or explosions, and we want the most mild conditions possible. And this is exactly where palladium on carbon and other related catalysts come in. In the presence of the metal catalyst, the hydrogen bond spontaneously breaks apart, and each individual atom attaches to the surface of the metal. This metal can also associate itself with a double bond and coordinate that to its surface as well. And one by one, it transfers the hydrogens to each side of the double bond, and it converts it to a single bond. This type of reaction is generally known as a reduction, but more specifically this one is known as a hydrogenation. Some of you might be wondering, why are we doing this with palladium on carbon and not just straight up palladium metal or some other metal catalyst? Well, by dispersing extremely fine particles of palladium on an inert substance like carbon, we're greatly increasing its surface area. And because surface area is directly related to the rate of the reaction, we're speeding it up quite a bit. So this reaction should work with something just like plain palladium powder, but it would be a lot slower. Some hydrogenations generate a decent amount of heat, but this one seemed relatively tame. There was no cooling or anything else that needed to be done, and I just let it sit here until it stopped absorbing hydrogen. The way that I knew it reached this point was because the balloon stopped shrinking. This usually isn't the best way to judge it though, because if there's any leak in the system, it will seem like the reaction goes on forever. But anyway, to end it, I shut the valve to the balloon and I opened up the one to my pump. Then I pulled a vacuum and I let the pump run for a few minutes to get out as much of the hydrogen as possible. When I felt that it was done, I closed the valve, took off the balloon, and refilled the system with air. This is something to be careful with though, because if the pump didn't pull out all of the hydrogen, the air could ignite some of it. It turned out fine when I did it, but I think that this part is best done with nitrogen. But anyway, now that the reaction was done, the next step was to purify out the raspberry ketone. So this whole setup was taken apart, and the first thing to do was to filter off the palladium on carbon and the sodium acetate. This was done by just passing it through some cotton in a funnel, along with some sea light. The sea light is basically just really fine sand, and it helps with the whole filtering process and to pull out the really fine particles of the palladium on carbon. After almost everything had passed through, I washed the flask and the stuff in the funnel with a bit more ethyl acetate. Then when that was all done, I did one final washing of the funnel with fresh ethyl acetate. I've never had an issue with it, but one thing to keep in mind is that palladium on carbon is pyrophoric, meaning it can spontaneously ignite in air. This can sometimes be even worse after the hydrogenation because some hydrogen gets stuck to the carbon. And what this all means is that it just has to be handled with care because it does pose a slight fire hazard. But anyway, with that all done now, I took away the funnel and I was left with this slightly yellow solution. This contained all of the raspberry ketone that I made, and to isolate it, I just had to get rid of the ethyl acetate. This was done pretty easily by just turning on the hot plate to a low heat and setting up a fan off to the side. Up until now, the smell was mostly overpowered by the ethyl acetate, but as it was evaporated off and things got more concentrated, I started to smell raspberry. It was a very faint, fruity and sweet smell, and it was a lot like blue raspberry candy. It all disappeared over the course of about 20 minutes, and eventually, when I stopped smelling ethyl acetate, I took it off the hot plate. I was left with this oily stuff, which I thought would crystallize as it cooled, but it just stayed as an oil. So to get it started, I got a glass rod, and I scraped the bottom of the beaker. It initially didn't look like much was happening, but slowly I started seeing crystals forming. Then over the next 30 seconds or so, the whole thing solidified. And using this rod, I was able to crush up most of it into this off-white, yellowish powder. Pure raspberry ketone is white though, so there are clearly still some impurities left over. However, from other runs, I found that it was really annoying to recrystallize, so I used a slightly different method. For this one, I added about 10 mils of water and brought it to a boil. I'm not exactly sure at what temperature this happened at, but eventually, the raspberry ketone melted into an oil. Pure raspberry ketone has a melting point around 82 to 84 C, so this happened probably in that area. I then boiled the water for a couple minutes, and I took it off the hot plate. I let it cool back to room temperature, but no crystallization happened, and it just stayed as an oil. Some chemicals can kind of be annoying like this. I mean, we saw that it was a solid before, but now that it's at room temperature again, it decided to stay as an oil. I had to force it into being a solid again, and to do this, I put it in the freezer. I waited till the water just started to freeze, and then I took it out and mixed it around. At first, it looked like it was still pretty stubborn and not much was happening, so I kind of gave up and turned off my camera. But then of course, when I wasn't filming it, it decided to solidify. Over the next couple minutes, I did my best to try to break up all the pieces. The thin rod wasn't working very well though, and I ended up changing it for a stopper, which was a lot better. All of the water was then removed by just a small gravity filtration. I also washed the beaker and the stuff in the filter with a small amount of extra water. When most of it was gone, I lightly squeezed it, and I left it out to dry. This was what I had the next day, and my total yield was 2 grams. This was extremely low, but I've done this procedure a couple times, and I always get close to the same amount. I'm thinking that maybe my 4-hydroxybenzaldehyde wasn't very pure, but I'm not sure. I could also just be bad at chemistry, but I prefer not to believe that. The incredibly low yield aside though, what did surprise me was how little this powder smelled. The odor was really faint and not overpowering at all, unlike some other compounds that I've made. I also wasn't getting any of that characteristic blue raspberry smell, and it was mostly just a sweet, fruity one. Because I wasn't able to do a proper recrystallization, I wasn't sure how pure this stuff was. I was also a bit concerned because when something fails to crystallize, it can sometimes mean that there are a lot of impurities present. To figure out its rough purity though, I just had to do something called TLC. To do this, I first needed a reference sample, which for a lot of projects can be hard or impossible, but in this case, it was really easy. As I mentioned in the intro, pure raspberry ketone is sold online, so I just had to pick some up. Then onto a TLC plate, I loaded a very small sample of this, along with some of the stuff that I made. This was done by dissolving each of them in a small amount of acetone, and they were applied using a very thin capillary. And when it was ready, I put it in a beaker that was preloaded with a 50-50 mixture of hexanes and ethyl acetate. I originally planned to do a small little TLC tutorial here, but this video has already turned out to be way too long, so I'm just going to show the results. When I looked at the finished plate under UV light, I saw that the spots were the same size for both the reference and the test, and they traveled the same distance. This confirmed to me that besides just going by smell, I did make raspberry ketone. Also, because there was little to nothing else on the plate, it told me that it was relatively pure. Now with all that confirmed, I felt comfortable moving on and trying to make the perfume. I initially thought that this might be a bit complicated, but I quickly found out that the general idea of perfume is actually really simple. You basically just need to take all the aroma compounds that you want and mix it with a carrier solvent. There are many different carriers that can be used, but the most common ones are just simple alcohols like ethanol or isopropanol. I went with 95% ethanol because it works well, but also because it's cheap and easy for me to get, and it's sold at my local pharmacy. So to get started, into a small vial, I added about half a gram of the ketone. Then I added the ethanol in small portions. I wanted to go just until the point that it all completely dissolved. I did this because I had no idea how potent it was going to be as a perfume, so I wanted to make it as concentrated as possible so I could dilute it later if I needed to. After a couple minutes, with more ethanol and a bit of shaking, it all disappeared and I was, well, basically done. To test it, I poured it into a small spray bottle and I shot the back of my hand. After letting the ethanol evaporate for something like a couple minutes, I can try smelling it, and it smells exactly like the dry powder did, which, doesn't really surprise me. It's just faintly sweet and kind of fruity, but it doesn't smell like raspberries. And I kind of expected this because when it comes to artificial scents and flavors, if you just pull out the major component from the fruit, the vegetable, or whatever you're trying to mimic, it's not going to be the same. You're going to get just one fraction of the complex smell or taste that you're trying to get. So for raspberries, I can try smelling this here, and it smells very different than the ketone, which is supposed to be its major component, but it's just missing a lot of other things which give the raspberry its characteristic smell. So when you're trying to make an artificial flavor or smell, it can be quite difficult. You can sometimes get away with just using a couple, but you'll often need several or even a dozen chemicals to get close to what you're looking for. There are, however, some exceptions to this, like with vanilla, which can be mimicked pretty well by just synthesizing its major component, which is vanillin. And that's what's used to make most artificial vanilla extracts, and most people can't tell the difference between that and the natural one. Anyway, I think that's about the end of this project. I honestly had a lot of fun with it, but making the raspberry ketone from scratch definitely wasn't very efficient. I ended up really liking the perfume part though, so I think in the future, I'm gonna try to make some more smelly compounds. However, I think I might venture away from nice and fruity smelling things, and maybe I'll get back into the nasty, stinky side. I'm thinking it might be interesting to do the opposite of making a perfume, and to instead try to make the worst smelling thing possible.